Hello, my name is Mr. McQuire and welcome to this presentation in the topic of forces. Today we are looking at the fifth lesson in this topic, and the subject we're looking at today is work done. So for today's lesson, let's make sure that we have found somewhere as free from distractions as possible to get on with the work. And you will need a pen and paper, and on it can you please put the title of a work done and underline it nice and centrally at the top. I'll just give you a minute to get that done. Okay, so as our starter, I'd like you now to use your piece of paper, and I'd like you to recall the different types of energy stores. And if you can, I'd like you to give an example for each one. So you've got a minute to try and recall as many energy stores as possible and give an example of each one. Okay, as we move through the lesson, you're going to see why this particular list is really important. So let's just have a look at that. We have got magnetic, and we can hold energy in magnets by pushing two poles that repel together. Got thermal, stored water, for example, in a hot water bottle. Chemical energy, which is obvious in things like a Mars bar, but explosives as well. Energy stored in a moving object. Electrostatic energy stored, for example, in a cloud in the sky, full of electrostatic charge. Elastic potential in a catapult. Gravitational potential in a ball that's at the top of a throw. And energy stored in nuclear power. Okay, so this is the same list again in more detail. Let's just be really clear about what it is that we're looking at here then. You should have a list of the energy stores that exist, and you should have an example of each of those. And you need to know those really well for today's lesson. Now, to move these energy stores between one another, which we're going to talk about today, we're going to use energy transfers to do that, and these are words that we're going to use to allow us to refer to the work being done in moving our energy stores from one form to another. So it is important that we understand these properly and that we have good examples. So if you need to pause the presentation to make sure those are complete, let's do that now. So let's look at our learning outcomes for today. Our challenge then is to be able to apply the relationship work done, measured in joules, equals force in newtons times distance moved, which is measured in meters. So as we should know from previous presentations that you've looked into, we need to make sure that the units are correct before we can do calculations in those, and we're going to be careful with those today. And then for our aspire to be able to describe the different energy changes that occur when work is carried out. So the word describe is critical there. So let's then apply that list of energy stores and energy transfers to a very important rule that we need to remember. And that's the law of conservation of energy, which states that energy can neither be created nor destroyed. It can only be transferred from one form to another. Okay, let's do a bit of application of the list that you have just made. So what happens when a rocket is launched into space? What I'd like you to do is to use the list and to identify energy changes that are taking place as that rocket lifts off. I'd like you to write a couple of sentences just to explain. Obviously it's going to start with fuel, just to give you an idea. And when you finish writing those sentences, we're going to turn it into an energy transfer diagram. If you already know how to do those, then just draw an energy transfer diagram for that. Then we're going to talk about work for the first time today. So you have got 2 minutes just to write a description or an energy transfer diagram of what's happening when a rocket is launched into space. Okay, that's a good length of time to have done some work. So you've got a title and you've done some writing. First of all, you should have written about chemical energy in the fuel. And if you've not done that, I need you to change the way that you think in terms of being able to address these changes in energies correctly. That's being turned into, first and foremost, gravitational potential energy. So there is an energy transfer diagram. It's a very basic one. But from what we've just said about the law of conservation of energy, then all the energy in the fuel ideally should be turned into gravitational potential energy. Now, because you're very clever and you look at that diagram, obviously there's an awful lot of light energy and there's an awful lot of sound energy being produced by that rocket, but we can't tell that obviously from the picture. Let's talk about work for a moment. So the transfer of energy is called work. I'd like you to write that down, please. So if you can start while I'm speaking to you. So therefore, if the transfer of energy is called work, then work done equals energy transferred. That's another way of putting it. So work done and energy are both measured in joules with a capital J. And then we have an example. So if you could just put that down, I'll give you a minute or so just to make sure those are down properly. Okay, so you should have finished your notes at that point. If you need more time, then just pause the presentation at this point. So let's just be clear, this is an important definition and you will be expected to use one or the other as we go through. So they could ask you to calculate work done, or they could ask you to calculate energy transferred, but they are equal to each other measured in joules. So for our challenge, we need to be able to use the relationship work done equals force times distance moved. Now I've said that because in this slide here it says the work is only done when a force causes the displacement or movement of the object. Now I'd like you to write that reminder down now and start writing. It does say that we're going to write a commentary for each of these diagrams, but what I would like to do is to just talk through them with you, because I think that we'll gain more by doing that. So first of all, I've added notes to these diagrams just so that we're clear about what has occurred. Starting with diagram A, I've written underneath that the car moves 5 meters. So therefore, if work done equals the force, then we have a push force from the girl who's pushing on the car, and we have a distance moved which is 5 meters. Therefore energy is being transferred, so therefore work is being done. Now looking at B, B is a very large boulder. I've not written any notes about that boulder in terms of it moving, so at this point I'm telling you that it's not moving. So the question of whether work is being done, first of all, there is no force being applied to that boulder and it is not moving. Therefore, there is no work being done in B. Now, C, the rock does not move. I've just clarified that underneath. We've got a very large boulder and a guy is pushing at the rock. Therefore, there is a force being applied to the rock, but there's no distance being achieved. Therefore, there is no work being done in that diagram. The guy will lose lots and lots of heat because of the sweat and the energy that he's using in literally trying to move that rock, but no work is being done. So the question that we're being asked at the bottom is what then affects the amount of work that's being done. And this is just straightforward logic. I want you to take your eye up to the top of the page for a moment. What affects the amount of work being done is answered in the equation. If we want to increase the amount of work, then we have to put a larger force through a greater distance. Or we could put a larger force through the same distance, for example. And all of those would increase the amount of work. Now, I hope that has helped clarify, because you've listened, exactly what is happening in each of these diagrams without writing an awful lot. Let's keep moving on. Okay, so now it's your turn to try and explain whether or not something is work. What I'm going to do now is I am going to ask you to say yes or no and to justify your answer. And the 5 questions I'd like you to answer, I want you to number as you go down your page. So the first scenario is someone climbing a ladder. The second is pushing a large rock 5 meters. Number 3, someone pushing a car really hard but they cannot make it move. Number 4 is someone in a lift going up 10 floors. And number 5, a parked car in a car park. And you've got 6 minutes to answer yes or no to each of those with the question number next to them, and I'd like you to justify your answer. Off you go. Should have finished the first question at least and be into the second. Okay, somewhere around the end of question 4 maybe, we're working into question 5. Last 2 minutes. Okay, so let's look at the answers. Hopefully you have applied some logic from the force times distance and looked for those in those scenarios. So someone climbing a ladder at 1 meter, yes, that person is moving a weight or force against gravity. Someone pushing a large rock 5 meters, yes, they are doing work against friction. Someone pushing a car really hard but they cannot make it move, the answer is no, because nothing has been moved. There's no distance involved in that. And number 4, going up 10 floors. Now, a person going up 10 floors, the answer is yes, because the lift motor has done the work. And number 5, a parked car. No, nothing has been moved in that scenario. So just look through the work that you've done for the last 6 minutes. If you need to pause the presentation and just think about those a little more and do some correcting, then do that now, please. So now we're going to look at work and energy, because work done equals energy transferred, and energy is measured in joules. If it's the same, work done is also measured in the same unit, which is the point that's being made here. To calculate work done, we use the following formula. Work done in joules equals force in Newton times distance moved in meters. And there's going to be an opportunity to write that down in a second. So it asks at the bottom, can you define what 1 joule is? So if I put a 1 in place of the force on that diagram, and I put a 1 in the place of the distance moved, then the work done would be 1 joule. So therefore 1 joule is literally a force of 1 Newton being moved a distance of 1 meter. Now let's do some application. It would be nice if we had lovely letters to put into the equation. So let's look at the application of the equation. You've now got a chance to write that down. It would be nice if we could summarize the equation so we didn't have to write all those words, and it would be nice if all the letters were obvious. Force is F when we write it out as a lettered summary. Unfortunately, distance is S, and we need to remember that. So therefore the full equation that we would write down is work done W equals force F times distance S. Don't forget when you write the equation in word form down to put work done in joules, force is in newtons, and distance moved is in meters. And if you happen to finish, then please, if you could rearrange the equation for F and for S, that would be good practice at this point. You've got a minute to do that. Okay, let's look at an example together first of all. Let's put this all up so we can talk through it. It's always good to get a proper example into our notes. So, first of all, the question. A cyclist pedals a bicycle with a force of 1,000 newtons, moving it 250 meters. How much work has been done by the cyclist? Now there's a force and there's a distance, so therefore work is being done. We've written the equation down. Work done equals force times distance moved, or W equals F times S. Put the numbers into the equation and done the calculation, and in this case the answer is 250,000 joules, or they have divided it by 1,000 to give us an answer in kilojoules of 250. Now again, if you're somebody that likes to have a great worked example in your notes, then I would ask you to pause the presentation at this point to do that. If you're happy to move on, then we will keep going and you can try some examples. We now have 3 questions to answer, do some application work. The easiest question on here is actually question C, so what I would like you to do is to answer question C first. I'll give you a minute to do that. When you finish question C, I'll insert a clip and you can watch as I answer that question. I'd like you to make sure that you put all the parts in. And then we'll do the same with B with a bit of an introduction, because there are little things we need to be careful of in each of the questions. So starting with question C, I'd like you to write down the information, the equation, and then to answer it. In this case it's in work done, so it should be in joules. So you've got 1 minute to do question C only. Okay, so let's look at how I answer that question now. Okay, let's kick off looking at part C, which hopefully is about a crane. This is probably the easiest question there. So a crane lifts a load of 5,000 newtons up 20 metres. How much work is done? So the first thing we need to know is the equation. Work done equals force times distance moved. The force this time is in the correct unit, which is 5,000 newtons. The distance moved is 20. And 20 times 5,000 is 100,000 joules. Or I could express that in kilojoules if it asked me. So divide by 1,000 should give me 100 kilojoules. Okay, starting on question B. Just notice that you have to convert centimetres into metres. It's a two-part question with parts 4 and 5, but that's basic mathematics that you are looking at there. Just don't be tricked up by the conversion. So you've got 1 minute now to do question B, and then watch as I answer it. Okay, I'm going to show you how to answer that, but if you need more time, just pause the presentation now. Let's have a look at question B. This is about Jack, who is climbing 20 steps and his weight is 600 newtons. They've then given us each step at 15 centimetres high, and it's told us that we must convert centimetres to metres. And the questions are for how much work is done on each step and how much work does he do to reach the top. So they've broken the question down to help us at this stage. So let's start off with question number 4. We know already that distance S should be measured in meters, but unfortunately it's in centimeters. So let's start off with a quick calculation. Let's just divide that, because there's a 100 centimeters in a 1 meter. So therefore 20 centimeters is 20 divided by 100, which gives us 0.2 meters. So that is the height of a 1 step. Now the question says eventually that Jack is going to climb 20 steps. So I'm just going to set myself up at this point and multiply 0.2 by 20, and that would mean that Jack had climbed 4 meters in total for the one part of the calculation. Okay, so let's go now for the first calculation, which is about a single step. Let's put the equation down. Work done equals force times distance moved. So W equals Jack, who weighs 600 newtons, and the distance is 0.2 meters. Put those into a calculator if you need to, and the answer is 120 joules. Now the next part of the question, question 5 then, is relatively straightforward now, because we now have to take that and we have to climb 20 steps. So therefore we're going to take the first part of the question, which is 120 joules, and we're going to multiply that by 20 steps from the question. I could have taken Jack's force, which is 600 newtons, and I could have multiplied it by 4 meters instead. And I'm now going to have an answer of 2,400 joules. Okay, now we're going to look at question A with 3 parts to this question, and I would point out to you this time that we have the mass in 1.5 kilograms. So from the previous presentation, using G as 10, you need to convert that into weight in newtons first, just to give you a hand with that. So you've got a minute to answer those 3 parts of the questions, and then I will run through it as I've done for the previous 2 parts. So let's go through question number 1 together. First of all, let's look at the question and get the information from it. It says that Chloe is stacking bags of flour on a shelf. Each bag has a mass of 1.5 kilograms and the shelf is 1.2 meters high. So in thinking about that question, the first thing we need to notice is that we don't have the correct units. We need to convert mass into weight, which you have covered in a previous presentation, and we should know that weight equals a mass times gravitational field strength. So in this instance we need to calculate the weight. The mass in kilograms is 1.2 kilograms, and we will take G to be 10 newtons per kilogram on this planet of ours. So W, the weight, then is 12 newtons. So that's what we're going to put into our work equation. So work done equals force times distance moved. Let's then put that into the equation. How much work does she do to stack each bag? So this is question number 2. So we now need to say that W equals 12 from the previous part of the question, times the height, which is a 1.2. And that then gives us a work done of 14.4 joules. So now we're on to part 3. It says there are 20 bags, so this is straightforward maths. It asks us to calculate the total work done. So the work done on one bag was 14.4. And now I am moving to 20 bags, so I need 14.4 of 20, and that gives me an answer of 288. So that is question. So we're now moving on to the Aspire part of our lesson, where we need to be able to describe the different energy changes when work is being carried out. Please remember that for work to be done, energy must be transferred. So right from the beginning of the lesson, when we asked you to write down energy stores, etc., that's where we've been heading to this point. So I'd like you to write down sentence number 1 and to think of the forms of energy and the transfers that are taking place for the gaps in 1 and then for 2. You've got a minute to do each one. Okay, let's look at our answers. I'd like you to fill in the gaps as we go, make sure they're correct. So looking at our possible answers, when a rower pulls an oar, the work done by the rower is changed into kinetic movement energy of the boat and heat energy by friction with the water. Number 2, a motor is used to raise a car park barrier, and as the key word, the work done by the motor is transferred into kinetic energy in motion, gravitational energy in the raised barrier, and heat energy. Would obviously be a bit of sound coming from that as well, but that's not a principal output. If you've put that in, I'll give you a mark for that. So we've had a good journey today, and we have spent quite a long time looking at an equation, work equals force times distance. We talked about the units, we talked about conversions, and we have applied that equation in many ways. And then for the Aspire, we've been able to describe different energy changes, which is where the lesson started today. So we've got a small true-false quiz to work through now. So for each of the following, I'd like you to decide if the description is true or false. You've got 1 minute to go through those and put a T or an F next to each of the numbers. So let's have a look then at the true and false quiz. Energy is transferred when work is done. Energy is transferred when work is done, so that would be true. The work done is greater than the amount of energy put in. That cannot be correct because of the law of conservation of energy. That's false. Work done equals force times distance. W equals F times S. Correct. Work is measured in newtons. No, that's not correct. That's false. That would be joules. The bigger the force applied, the bigger the work done. Yes, if the distance is a constant. True. Work done to overcome friction often changes into heat energy. Is correct. Work is 150 joules when a force of 10 newtons moves something 15 meters. Well, 10 times 15 is 150. So therefore, in summary, 1 true, 2 is false, 3 is true, 4 is false, 5 is true, and 6 is true, and finally 7 is true. Just check those against yours and see how you've done. So finally, welcome to our last slide. So for our challenge, we were to be able to calculate work done, which equals force in newtons times distance in meters. And for our aspire to be able to describe the different energy changes when work is carried out. I'm Mr. McQuire. It's been a pleasure to share this presentation with you today, and goodbye.